If only that would happen on the WAL.
Okay, I think I am live.
You good?
And I don't know if you can see, but you all are on the screen for a second. So just so you know, and it's 20 seconds delayed, which is interesting. I have Inception. I can see myself and then I can see the live stream and then I can see us in the live stream. 20 seconds delayed.
Oh, this is weird.
As long as you're not having to listen to yourself 20 seconds.
Yeah, exactly. I think I'm on like the viewing part, so that's nice. So I'm gonna minimize that because
As long as it's not 20 seconds in the future, that'd be even worse.
wouldn't it? It might be useful actually for me. I can know what question's gonna be asked.
Morning, Gary.
Hi, Gary.
Hey, Jim, take a look at your email.
Do
We just
have
caught
to?
a photo with you at the Capitol in January.
Oh, no, that wasn't me.
It was you. You had a Confederate flag.
Hey, Gary, you do realise by doing that sort of thing, I'll probably expect the police to arrive in my door in about 25 minutes.
Well, and it would be a good thing, wouldn't it?
Oh, thank you. This is being live streamed now, Gary, all around the world, by the way.
Yeah. This will be all right. So I think I
All you
should
can say is,
probably
I'm English. I don't know what a Confederate flag is.
It's only 'cause
Gary, I have my page numbers.
you lot didn't want to pay your taxes. You still not want to do them.
I thought it was funny that you emailed me that, Gary, because I've been learning from you for the past 6 years. There's no way I was going to forget to put my page numbers on.
Good, good. The point is, I'm the type of person who, as I go through your talk, will copy down the page number and then make notes on what I want to ask.
Mm-hmm.
There are no page numbers, and I have to send you on a wild goose chase to find things.
Yep. I'm the same way, though. I learned it from you.
So are you actually at a new job now, no matter where you happen to be physically?
No, I'm in Texas just doing the PhD, and then hopefully at the end I can start my postdoc. So, but yeah, I'm not in Illinois anymore.
Okay, and the postdoc will be at least technically where?
Across a couple of universities at Rice, at Texas A&M, and UT.
Okay, well, in today's age, you don't have to be at any of those places.
Exactly.
Although that's
Sort of
unfortunate.
taking advantage of it, I guess.
Well, I'm looking forward to COVID vaccination passports.
Mm-hmm. That's really what it is. Okay. I hope that I'm streaming. I'm fine. And then I can go, if you'd like, I can share my screen.
Yeah, go on.
If you don't share your screen, it'll be,
That would be bad, wouldn't it?
Do that first, and then we just give people a minute, Julia, then I'll introduce you and then go from there. Is that okay?
Yeah, that's fine.
Okay, lovely. Got a young
Okay, so
viewing
you can
audience.
see that?
Yeah, that's perfect.
Perfect.
Yeah, got captioning on as well.
Yeah.
Okay.
Cool. And I'm going to give it a little bit of time because I think a few people are still going to be jumping in. A couple of people actually jumped in at 10, Jim. And I think it's because in the UK and in Europe, there was the time change already.
Yeah, it was. Their clocks went forward on Saturday night. They're 2 weeks behind us. Yeah.
Uh-huh. So I realized after like 2 or 3 people, I was like, oh, it's daylight savings for them. So.
Right. Okay. Yeah, it did. Okay. Okay, we'll give them a couple minutes.
Yeah. So I'm going to give them a few minutes just to catch on.
Do you get to see how many people are joining in live streaming? Presumably not, or do you?
That's a good question. I should check.
as long as we're talking about time zones and things, I have a funny story for you.
Go ahead.
Go on.
The United States has 4 time zones, excluding Alaska and Hawaii. China, until 1949, had 5 time zones. But since then, it has exactly 1 time zone. And I happen to know the reason for that. But once I asked my students what was the reason for that, And he said, Chinese peasants don't even know how to read a clock. Don't confuse them more than necessary.
That's true, though. I could see how that would be really confusing.
But it was
Everybody
true.
starts their day an hour earlier, an hour later, and you have no idea why. All right, can you all see this bar above my screen?
Yeah,
I see a bar.
That's annoying.
it's okay. We can see your
It's
cursor.
very small.
We can see your mouse as well, though. So that's
Mhm.
good. Yeah.
Oh yeah, let me put my pointer.
Okay.
All right, can you see that pointer?
Yeah, it's good.
Cool.
Okay, Julie, should I start now? Just
Um,
anybody else to come in?
I think that there.
I've got a few things to say just to
Yeah, that's fine. Go ahead.
warm us up as well. So yeah, let's start. Hey, hi folks. Well, it's just gone 11, so let's make a start. And firstly, welcome to everyone to Julia's PhD colloquium. Welcome to all our friends and colleagues from across the globe. I know quite a few are going to tune in today. Actually, and a special welcome to our family are tuning in today, and I know they must be very proud of Julia at this moment. So let me just say a few words to introduce Julia before I talk. I think it was back in 2014, I think it was, Julia, you emailed me first
Yeah.
and said she'd been so enthused by work that she'd done with Ryan Ewan at an undergrad at Texas A&M that wanted to know if I would be interested in taking in any graduate students who are interested in dunes. And I think it's fair to say that sort of inquiry is rare. And I said, yep, of course. And I know then I met Julia at AGU at San Francisco that year, and we chatted, and luckily that ended up with Julia and Nate coming to Illinois, arriving in 2015. And I know within just a few weeks of that, Julia and I were meeting with our colleagues in the Yellow River in Zhengzhou, discussing potential work on the Yellow River. And all of that work, was then followed by lots of collaborations with colleagues from Brazil, the Netherlands, US, UK, and I'd like to thank them actually for all they've done actually for Julia's journey and assisting in many ways for the research. So just a couple things to finish. I'd like to say three things about Julia actually. The first is actually Julia's enthusiasm and devotion to her work actually have never swerved in the last 3 years, 4 years, 5 years. And it's been exciting to watch her grow and develop and tackle a whole range of research concerning river dunes. And with that sort of enthusiasm and devotion, I think they've been infectious. And the teamwork and collaboration that Julia has undertaken has been key to all of that. And she's been just a fantastic team member. I think second, the other thing I think it's fair to say in the last 18 months, Julia's journey has in some ways been a disaster. And I say that very kindly because Julia's undergone the journey that many folks have had in the last year or so with COVID and the like. So Julia had many delays in her lab work and overseas travel. The hydro lab that she was originally going to do some work in, and thanks to Marcelo and Andy for all their work there, began to undergo major redevelopment and rebuild. I think part of the roof fell in, Julia, was that right?
Yeah.
Lots of delays there. And literally just as Julia was ready to go and ready to perform the experiments that she'd planned, COVID hit, and all of that was cancelled. So new plans were made. Julia then moved back to Texas last year to complete her writing up. And I think just as it was nearing its end, the meeting of a polar vortex and the inability of Texas to operate a proper electricity system then meant several days in the cold without power. I say all this to highlight that Julia's coped with and actually flourished with many things in the face of adversity. And I think that's a real testament to actually what she's done over the last few years. And very lastly, I've just got to highlight that actually Julia's been a really outstanding departmental school and university citizen. And Julia's become involved in a whole range of things at Illinois that actually just made our community better. She's had roles in different graduate councils and committees at a university level. She had a key role in helping establish geology within the engineering open house. She organized jointly the Hydro SEDS group, which has been really important for us. She's mentored children at local schools. And she did a truly amazing job with Aida in GGIS of devising and organizing the girls' summer camp, science camp. And on top of all this, Julia's been playing a role in the Geo-Latina community and also in developing anti-racism plan for the geosciences, which was awarded a presidential citation last year by the AGU. So all of this is just to say that, you know, impact is actually far more about other things as well as just your research and the imprint that you leave on your community. And Julia's made a fantastic contribution to that here. And we're very proud of the long-lasting impact that she's actually had on Illinois and the broader community. So without further ado, Julia, let's turn it over to you and let's hear about some of the exciting science you've done in your PhD concerning the morphology of alluvial sand dunes.
Wow, thank you. Thank you, Jim, for the wonderful introduction. Before I begin, I want to share a story with you. So when I was in high school, I loved science, but I didn't really know what that meant in terms of a career or really what I could do with that. And so in high school, my biology teacher recommended that I apply for this program to study or to go to Texas A&M and to learn about geosciences. It was a program specifically for underrepresented students. I didn't really know what that meant, but I was like, okay, sure. And I went and I experienced one of the most pivotal moments in my life. I spent 3 days learning about geosciences and I just thought, wow, this is so cool. I could definitely do this. This is something that I could love. And in this moment here, I was sitting at an 8 a.m. Geology 101 lecture. And I was really tired. I was not used to 8 a.m. lectures. I was a high school student. This was not normal for me. And I was kind of sitting in the back and I was kind of falling asleep. And the professor puts up this picture of these structures in this rock. And he says, these are Aeolian dune sedimentary structures. These tell us not only that this was an ancient dune field, but the direction that these lines point towards tell us the direction that the ancient winds were blowing. In this moment, I thought, this is the coolest thing ever. And I made a goal. I made a goal for myself that I was going to go to Texas A&M University and I was going to learn more about these sand dunes. So I did. I went to Texas A&M University, and during my time there, I conducted undergraduate research. I studied sand dunes on Earth and Titan, and I was very lucky to submit this work and publish it in the Texas A&M undergraduate journal. And I was also very lucky to go and see sand dunes for the first time in field camp. From this experience, I realized I really loved research and I wanted to do this more. And so I decided that I wanted to go to graduate school. So during my search, I found Illinois and I found Jim, and we decided, wow, we could really do a cool project together. And so I decided that I was going to move to Illinois and move from Texas to Illinois, move from Texas A&M to University of Illinois undergrad to graduate school, but also move from studying desert dunes to studying river dunes. And so what I'm going to talk to you about today is what I've accomplished in the past 6 years doing that. I'll start off by giving you some of the basics of dune morphology and flow dynamics. Then I'll talk about the shape of dunes in the world's big rivers, the possible mechanisms of formation, and the implications, which is what my PhD research is mainly about. And then I'll finish by discussing a little bit about how I'm becoming a future leader in geosciences. And so we know that dunes exist in a variety of environments. So for example, these are Aeolian dunes in White Sands, New Mexico. These are fluvial dunes that are at the bottom of the river. And especially these dunes are shown here because this river is tidally influenced. And so this is during low tide and we can actually see the dunes exposed. We also know that dunes are preserved in the rock record through what we call cross stratification. And so this is an example of cross stratification. This is actually what I had seen that first time in that Geology 101 lecture. This is what really got me hooked. A future leader. And so when we talk about dunes, we have to remember that dunes are a three-dimensional surface, but very often it's easy to talk about them in terms of a profile. So a profile, you can imagine we're taking a 2D slice out of this dune, and we're going to trace the elevation along the distance of the dune. And so you can imagine that we would get out a graph that looks like this, where we have distance versus elevation, and we have a line that is tracing the elevation. So if we look at a simple dune profile, this is often what we would see. We would see a gently sloping stoss slope. The top of the dune is the dune crest. Then we would have a steeply sloping lee side, which is often thought to be sloping at around 20 to 30 degrees. And then we would have the bottom of the dune, which is the dune trough. These dunes can range from 0.5 meter to 10 meters in height and 10 to even hundreds of meters in wavelength. Oftentimes in rivers, we have superimposed dunes that climb up the stoss of these dunes. And as this dune moves forward and sediment is deposited in this lee side, we get the development of stratification, which is how those dunes will be preserved in the rock record. If we look at some basics of the flow over these dunes, as flow moves over the stoss side, it will detach at the dune crest and reattach down here near the dune trough and on the following dune stoss side. In this area, we would have a flow separation zone, and a shear layer would develop between this flow separation zone and the wake region. When flow reattaches, we would have the development of an internal boundary layer, maximum flow velocities on the top of the dune, and expanding flow velocities on the bottom, above the bottom of the dune. When flow detaches here, we actually will have turbulence advected off of the crest, where Kelvin-Helmholtz instabilities are developed in the shear layer, and we would see that on the water surface as boils coming up from the water surface. This is a great image, and I think it shows the basics of the flow dynamics well, but I like to show this in a video because I think it's really cool to watch. So if we look at Mark Schmeichel's YouTube here, what we're looking at is flow. High velocity and low velocity is in this bluish kind of color. If we look at the stoss side, we see that flow is coming over, it detaches on the dune crest, and we get that recirculation in the lee side. So from this image, you can see that this lee side is very important in determining the magnitude of flow separation and the turbulence that is created. Now, the lee side is interesting because previous work has shown us that dunes have complex shapes and their lee sides are often segmented. You can see that from this image here from Alice Lafer's work in 2016, where she measured the different shapes of dunes in the Paraná, and she found that dunes have 6 different stoss sides and 4 different lee sides. So you can see that this lee side is not simple. It's not just a straight line. We can see that in dune profiles from the Paraná River. So we have distance on the X and depth on the Y. Flow is going from right to left here. At the Paraná River near Aguas Corrientes, you can see that these dunes are sort of hump shaped. Whereas if we look at the dunes near Paso de la Patria, we can see that we have a very defined stoss side and a pretty well-defined lee side. We also have some superimposed dunes climbing. If we look at dunes from the Vaal River here, flow is going from left to right in this case. We see again, we have this well-developed stoss side and a very well-developed lee side. We also have some superimposed dunes. And this lee side, it looks like it's sloping at a pretty high angle. But if we actually take into account the actual ratio of this graph, distance versus depth, and we measure the real lee side angle, we see that that lee side is only sloping at 11 degrees. That is very different than what we previously thought. We often think these dunes are sloping at 20 to 30 degrees. The fact that this is sloping at 11 degrees means that these are low angle dunes. So low angle dunes are important and they're interesting because there's evidence for a different fluid dynamics in low angle dunes. Specifically, there's evidence for a lack of or an intermittent zone of flow separation in the lee side. What do I mean by that? So here's a great example. This is showing a rotating wing that depicts the onset of flow separation. So you can see as the angle of this wing increases, we develop a bigger flow separation zone. So here, let's watch it again. This wing is at a low angle and we don't have any flow separation. As it increases, we develop flow separation. And as this angle increases to a greater value, we can see that the flow separation grows bigger. And so previous work has looked at the flow separation in a dune lee side, and the consensus is that permanent flow separation is absent for lee side angles that are less than 10 degrees. In addition, we know that dune size is important in big rivers. And the idea that we often have is that dune size is related to flow depth. So here we often think that flow depth is about 3 times the dune height. That means that in big rivers and deep flows, we should see large dunes. And that's kind of what we see when we look at the Paraná River. We can see that these flow depths are up to 12 meters. The dune heights that we see from this bathymetric map here are up to 2.5 meters, and their wavelengths are 85 meters. In the sedimentary record, understanding the size of dunes is also important because the size of dune cross sets may be proportional to flow depth. And so the idea here is that dune height is about 3 times the size of cross set thickness. What do I mean by cross sets, cross stratification? This is a great image from Jack Brown's senior thesis where he was running dunes and seeing what the stratification would be behind. You can see that as these dunes move forward, they're depositing in their lee side and they're leaving along these lines. These are similar to what we see in the Amazon River from cross stratification. And so understanding dune size and flow depth relationships is essential to predicting the paleohydraulics of ancient environments from outcrops. Now, only recently has the bottom of the world's big rivers been revealed, and this is through the use of multi-beam echo sounder. So multi-beam echo sounder has been used a lot in marine settings. You can imagine that we have a big ship here, we have a multi-beam system, and that multi-beam system sends sound waves down to the riverbed. The time it takes for the sound wave to go down to the riverbed and come back tells us a distance. And when we do that across the entire, in this case, seabed, we can reveal the bathymetry. And so using this on the world's big rivers has completely changed our view. It's shown us that dunes in the world's big rivers are prevalent, and they're the major contributors to sediment transport. In this image, we're looking at dunes at the bottom of the Paraná River, and you can see that we have just dunes moving through, ribbons of sand moving through these rivers. Now, when we have all of this beautiful data, we now need a way to measure the dunes. And so in my PhD, I created the bed form analysis method for bathymetric information. We're going to call it Bambi for short now. Now, what Bambi does is it measures the dunes across the entire width of the river, and it outputs measurements of the dune height, the lee side angle, the wavelength, the lee side shape, and the flow depth. And the really cool thing is that Bambi georeferences the data points to the trough of the dune, so we can do some really cool spatial analysis as well. Let's zoom into this image here. You can see that these lines are actually individual points, and they're plotted in the trough of the dune. And so what this has done is it increased our data output from maybe a couple hundred value measurements that we would do by hand to tens of thousands to even hundreds of thousands of measurements. Very briefly, I'll discuss how Bambi works through a visual description. So what we use is the multi-beam map, which is the bathymetry. And from that, we create a slope map and an aspect map. The slope map tells us the angle that a surface is inclining to, and the aspect map tells us the direction that the surface is pointing towards. Specifically, we use the aspect map, and we say if a surface is pointing plus or minus 40 degrees of the flow direction, it's a lee side, and if it's not, it's a Stoss side. We use the difference between the lee sides and the Stoss sides, where if we see a point between a Stoss side and a lee side, that's a dune crest. And if we see a point between a lee side and a Stoss side, that's the dune trough. By knowing the dune crest and the dune trough, we can measure the dune height, the dune wavelength, and we can measure the dune lee side. Now, Bambi measures the lee side in a few interesting ways. I think this is best shown through a picture here. So we have flow going from left to right here, and you can see in this image, this is a simple dune. And so Bambi measures the lee side of the simple dune a few different ways. It measures the mean angle, which is this blue line, and it measures the maximum angle, which is this red line. And you can see, because this is a simple dune, the lee side is simple and the mean and the max angle is the same. But if we have a weird shaped dune, specifically if we have a lee side that has a couple of different segments, Bambi measures the mean angle, but it also measures the maximum angle. And you can see from this red line that the maximum angle is different than the mean angle. And so Bambi not only measures the mean and the max, but it also tells us where this maximum slope is. Is it at the top of the dune, or is it at the bottom of the dune in this case? And so what I'm going to show you first is how we've used Bambi to understand the shape of dunes in the world's big rivers. Now, this work was made possible through teams of a lot of different groups who have spent the last 20 years acquiring multi-beam from a variety of the world's different rivers. And I was very lucky to come at a time where everybody was excited to share their data and work together. And so we were successful in publishing this work, where we studied the shape of dunes in the world's big rivers, including the Amazon, the Paraná, the Missouri, the Vaal, the Mississippi, and the Mekong rivers. In this research, what we wanted to know was what do dunes in big rivers look like? What is their shape and what is their size? What can their shape tell us about the relationship between hydrodynamics and sediment transport? And can their shape help us understand what big dunes may look like preserved in the rock record? And so what I'll show you first is dune lee side angle measurements. So here we are looking at a lee side histogram. So we have values from 0 to 40 degrees, and we have percentage on the Y. We have mean angle, and we have the maximum angle. We're looking at data from the Amazon, Mekong, Mississippi, Missouri, Paraná, Vaal, and then at the bottom, all of the rivers combined. If we look at the mean lee side angle, this blue line is actually 10 degrees. And we can see that majority of the mean lee side angles are at about 10 degrees. A lot of these values peak at around 10 degrees. And so these dunes have mean lee side angles around 10 degrees. When we look at the maximum lee side angles, we can see that the maximum lee side angles are a little bit greater than the mean angles. But if we look at this shaded area here, we can see that majority of the maximum angles don't really fall there. And that's interesting because this is 20 and 30 degrees. And this is what we often thought that dune lee side sloped at. And so what this tells us is that dunes are dominantly low angle in big rivers. When we look at the location of the maximum lee side slope, for example, if we have a dune that looks like this one up here with a high slope on the top of the dune, if we were to plot that in terms of a histogram with the location of the maximum slope on the bottom, we would see that the histogram would be shifted towards high values. Now, if the maximum slope is on the bottom half of the dune, we would see that the histogram would be shifted towards lower values. And when we look at the histogram that tells us the fractional height of the maximum lee side slope, we see that it actually peaks at about 0.4, which tells us that the maximum lee side slope is commonly located towards the lower middle half of the dune lee side. And this is important for two different reasons. This tells us that flow separation may be less significant with the brink point on the lower half of the dune lee side. And also, the maximum slope is more likely to be preserved if it's on the lower half of the dune lee side. Now, if we look at dune height versus flow depth, remember this is really important when we try to make paleohydraulic reconstructions. So if we look at flow depth on the X and dune height on the Y, we've plotted every single dune in all of these rivers and their relationship with flow depth and dune height. This dashed line here is that dune height is 1/3 of the flow depth. This is often what we think when we think about the relationship between dune height and flow depth. We can see that a lot of these points are below that. And if we actually plot that in a different way, if we plot H over Y in a cumulative plot, we can see that the H over Y 90 up here is about 0.127. So that means that 90% of the dunes are at or below H over Y equals 0.127. So that tells us that whereas dunes with heights up to 10 meters do exist in deep flows, smaller dunes are much more common in these channels. Now, finally, in these big rivers, we want to know the potential for flow separation. And so we can view that in this way. If we look at this plot, we have the x-axis, which is lee side angle, and the y-axis is the relative dune height, the dune height over the flow depth. So if the values plot in this area here with lee sides less than 10 degrees, we will see no permanent flow separation, and that's from the literature. And if the values plot here with lee side angles greater than 24 degrees, then we will see fully developed permanent flow separation. Now, in between 10 and 24 degrees, we know that the flow separation potential will be increasing, and a flow separation zone will be growing. And whenever we have values greater than this dashed line, we know that that is the onset of permanent flow separation. So when we look at this data, because a lot of the values, which are shown here in red, plot down here, it tells us that flow separation potential is low for all of these dunes and these big rivers. And this requires that we reassess how we incorporate flow separation in models that seek to predict flow resistance, water levels, and even flood risk. So to summarize this work, we saw that low angle dunes are dominant in big rivers and deep flows. We know that the maximum slope is more commonly located on the bottom half of the dune lee side. We saw that smaller dunes are common in deep flows, and the H/Y relationship is more likely 0.127. And we see that dunes in big rivers have low potential for flow separation due to their low angles and their small relative dune heights. So these morphological characteristics and their influence on fluid flow have profound implications for the models of flow, how flow resistance is predicted and modeled, and how the deposits of such dunes are recognized in the rock record. So for example, if we look at models that are trying to predict the turbulence kinetic energy in the dune lee side, so we'll look at this bottom panel here. These are for dunes modeled over a 10-degree lee side, a 20-degree lee side, and a 30-degree lee side. So let's focus on the turbulent kinetic energy, where blue is low turbulent kinetic energy and red is high. If we look at the 10 degrees case here, we see that there's really very low turbulent kinetic energy. And this is what we would expect from big rivers, because these big rivers have lee sides at around 10 degrees. But what's interesting is that if we look at the models of 30 degrees, we can see that we have a lot of turbulent kinetic energy. And that's interesting because this is what we use in current models. So you can see that there's a disconnect between what we see in big rivers and what we're using to model them. Now, if we look at recent deposits, for example, here in the Bermejo River, this is taken through echo sounder lines that can sort of penetrate deeper into the substrate and tell us what these recent deposits would look like. We can see flow is going from right to left here, that we have lee side angles from 6.12 degrees, 4.48 degrees, and we even have some low angle lamination at 1.72 degrees. So you can imagine that these low angle lee side angles are very common with very shallow dips, and this would be very difficult to tell the difference between a low angle strata compared to something that's flatbed, even though the interpretations that we would make between those two would be very different. Now, the next question is, now that we know what these dunes look like, how can we use these shape parameters to understand the mechanisms that lead to shape complexity? Now, there are a few mechanisms that have been proposed to create low angle dunes. The first being the influence of dune superimposition, where we could have complex flow interactions between small scale and large scale dunes, where the small scale dunes can actually influence the large dune shape. The second being the influence of sediment suspension, where we could have so much sediment in suspension that it actually bypasses the crest and deposits in the dune trough, which would lower the dune lee side. Or we could have so much sediment in suspension that it actually dampens the turbulence, which would allow more deposition in the dune trough, therefore lowering the lee side. Finally, we could have the influence of lee side avalanches and grain flows controlled by flow depth, where in deep flows, these lee side avalanches can actually become liquefied, and they can travel further down the lee side, promoting low angle dune growth. So I'm actually going to go in and talk about each one of these piece by piece, and we're going to start from the bottom with lee side avalanches. So lee side avalanches, the hypothesis here is that these liquefied avalanches, which occur through excess pore pressure in deep flows, can move further down the dune lee side and into the trough, which promotes low angle dune formation. So for example, this is a schematic from Kostashik and Vendetti. In this A panel, you can see how these avalanches would occur. we would have a wedge of sediment developed and then an avalanche where the sediment would break and travel down the lee side. If the lee side is if the avalanche is granular, we could see that that lee side won't travel very far down the liquefied avalanche, or the granular avalanche won't travel very far, and we'll have the promotion of this high angle lee side. Whereas if the avalanche is liquefied, it would travel further down the lee side and we would have the promotion of this low angle. Now this is a hypothesis, and so that means that we need to assess it with real data. So if we look at data from the Amazon River here, we have dune height and flow depth on the X and lee side angle on the Y. We can see that majority of these dunes have low angle lee sides at around 10 degrees. But if we look at the values up here, we can see that we have a good amount of high angle dunes at a range of dune heights and flow depths. And if we look at this other data set from Galeazzi in 2018, we can see in this case for flow depths from 20 to 40 meters, we have a range of lee side angles from very low angle all the way up to pretty high angle. And so the fact that we see high angle dunes in these deep flows means that liquefied avalanches cannot be the dominating control. Now, if we look at the influence of sediment suspension, again, the idea here is that we could have so much sediment in suspension that it actually bypasses the dune crest and deposits in the dune trough, which would promote low angle dune formation. And also we could have so much sediment in suspension that it would actually dampen the turbulence, which would enhance sediment deposition in the dune trough and lee side, which would promote low angle dunes as well. So sediment suspension has been looked at in a few different ways. Often we look at it in terms of this suspension number. The suspension number is the ratio of the shear velocity over the particle falling velocity. And so when that value is greater than 1, it tells us that extensive suspension is occurring. So if we look at these plots from Nuxbun and Hoytink and Bradley and Vendetti, we can see that we have suspension number on the X and a value of relative dune height on the Y here, dune height on the Y, and then dune height over wavelength on the Y in this plot. We can see that when suspension number is increasing, we have an increase in the dune height. And then when it equals 1, we have a decrease here. We see the same thing in dune height from Bradley and Vendetti, and we see the same thing from aspect ratio, height over wavelength from Bradley and Vendetti. So this tells us that suspension at least is controlling or influencing the dune size. Now, Nuxbun and Hoytink took this a little bit further, and they wanted to know what the influence of slip face angle was, or how slip face angle changed between bed load and suspended load cases. And from these histograms, we can see that the lee side PDFs show us that dunes and suspension dominated cases have low angle lee sides compared to the bed load dominated cases. So for example, we have values at around 20 degrees here, but here we actually have a good amount of values at around 10 degrees in the suspended load. So I wanted to take this a bit further, and I wanted to understand what the potential transport controls on dune lee side angle could be. And as Jim told you, we had a lot of problems with some of the lab stuff not working out and this and that. And so the resilient graduate student that I am, Jim and I found a really awesome data set to look at to answer this problem. We found through Bradley and Vendetti that they had these maps that were freely available online of dune development all the way to equilibrium across a range of transport conditions from the threshold of sediment motion, bed load, all the way to suspended load. And so to give you an example of the difference in these kinds of transports, if we look at bed load cases, this is a video showing bed load transport. You can see that these particles are moving along the bed. They're saltating along the bed. Whereas if we look at suspended load, you can see that the suspended load means that all that sediment is just moving through the water column. So you can see how those different transport cases could actually influence this production or the shape of the dunes and the dune lee side angle. And so what I did is I ran Bambi on all of those maps, and what we're going to look at is the equilibrium case. So here what we're looking at is flow depth over mean lee side angle, and we can see that dunes range in lee side angle from 10 all the way up to 30 degrees across a range of flow depths. from 15 centimeters all the way to 25 centimeters. If we look at the lee side angle with respect to suspension number, we can see that the lee side angle decreases when suspension number is greater than 1. And we can see that here from these values across this solid line. Now, the cool thing about Bambi is because we have so many measurements across the range of all these experiments, we can look at lee side histograms. What we're looking at here is lee side angle histograms for all of the cases in the bed load dominated and the suspension load dominated experiments across flow depths from 15 centimeters, 20 centimeters, and 25 centimeters. And what I want you to see here is that if we look at the difference between the suspension load cases and the bed load cases, we can see that the suspension load cases, in the suspension load cases, the lee side angle is lower than in the bed load dominated case. And to push this just a little bit further, we see from this case of the 15 centimeter flow depth that low angle lee sides form in shallow flows. Now, the final idea is that the influence of bed form superimposition can have an effect on the lee side angle. So here we can have bed form amalgamation, which can produce erosion of the dune crest and the dune lee side due to bed shear stresses generated in the lee of the superimposed bed form. What does that mean? So let's look at this a little bit closer. The idea is that when we have a bed form, for example, here, that is greater than 0.25 of this large dune height, then it can actually influence this large dune by eroding the dune crest and creating a low angle reactivation surface, which reduces the lee side slope. So I assessed this by using the experimental data from the threshold condition in the 15 centimeter flow depth. You can see a few of the maps here from the Bradley and Vendetti experimental data. And what I've done is I've taken a center line across the map. And what we can see are these profiles. We're going to focus on this dune here that's highlighted in yellow. I've also plotted the lee side angle of the big dune and the smaller dune. The big dune is in blue and the smaller dunes are in gray. And I've plotted the ratio of the superimposed dune height to the large dune height. So we're looking at time equals 160 minutes all the way through to time equals 250 minutes after equilibrium has been reached. Now, if we look at time equals 190 minutes, you can see that this dune lee side angle is pretty high. It's around 25 degrees. And then we have the development of these superimposed dunes. The ratio of HS over HL is near 0.25 here. We can see that. And when those superimposed dunes move over the larger dune, we see a reduction in the lee side slope. This reduction continues all the way through to time equals 220 minutes, and it decreases the lee side slope to 10 degrees. We can see that here from this profile. So what this tells us is that dune lee side angle begins to lower when the HS over HL is close to 0.25, and it lowers by a pretty good amount. It lowers by about 16 degrees. So when we think about the possible controlling mechanisms that create low angle dunes, we can say that the influence of liquefied avalanches is likely not a control. And that's because we see high angle dunes in deep flows, and we see low angle dunes in shallow flows. Instead, it's more likely that the influence of sediment suspension and bed form superimposition are controls that are controlling mechanisms that can create low angle dunes. And there's likely a balance between the two, where when one is dominant, the other one is less likely important. Now, what does this mean in terms of flow separation potential? When we look at cases on the bed load dominated experiments and the suspended load dominated experiments, we can see that the flow separation potential is greater in the bed load dominated case than in the suspended load dominated case. And so that's really important for us to continue with when we think about flow separation potential and the potential roughness that these dunes could create. Now, how does this come together when we think about natural rivers? So I've been trying to understand this by studying the River Vaal, which experiences variable flow. This is an example, this is a picture of me standing on the banks of the River Vaal near Nijmegen. And you can see in this image here, this is a boat behind me. The River Vaal is a very, very important shipping canal where boats travel daily from the North Sea through the River Vaal to Germany. because it's such an important shipping canal, the Dutch government really want to know how the riverbed is changing and whether certain areas are grading too high so that a ship can safely travel by. And so because of that reason, multi-beam data has been surveyed in the Vaal River for the past 15 years, every 2 weeks. And I've been very fortunate to be able to work on this data set through working with Dr. Tyan van Dijk of Deltares. Before we start talking about the River Vaal, I want to sort of just explain this concept, which is called bedform hysteresis. The idea here is that we know rivers experience variations in flow discharge, flow depth, water surface slope, all that together create variations in bed shear stress. When we think about a flood, if we look at time on the X and discharge on the Y, when discharge is increasing with time, we have the rising stage, then we have the peak of the flood, and then when discharge is decreasing with time, we have the falling stage. Now, because of these variations, we know that dunes take longer to respond in changes of flow due to a sediment transport lag. And when we look at how that, we look at what that means in terms of a flood, we see that dunes often are larger during the falling stage than they are on the rising stage. And you can see that from this plot here. We have bed shear stress on the X and dune height on the Y. And we can see that during the rising stage, dune height increases, and during the falling stage, dune height decreases. But we can see that over the same bed shear stress, we have a greater dune height in the falling stage. Why is this important? Well, you can imagine that during the flood, when the dunes grow, in the falling stage, when water levels is dropping, but the dunes are still big, that can create a very dangerous time where we could have critical water levels and ships could potentially run into these big dunes. And I don't know about you, but I do not want to see the bill for that dredging cost. The other interesting thing about the River Vaal is that there's an interesting shipping trend. When ships travel from Rotterdam up to Germany, they travel on the southern side. They travel very low into the water column because they're really heavy. They're carrying a lot of goods. When they go to Germany, they drop everything off and then they travel back to Rotterdam. And you can imagine that they're a lot lighter when they travel back to Rotterdam and they travel on the northern side. So they travel a lot higher into the water column. Because of that, Wilbers and Ten Brink have seen that there's a difference in the scale between dunes on the northern side of the river and dunes on the southern side. So because of that reason, I'm going to focus on dunes on the northern side. Now, if we look at the River Vaal, just a very brief summary here. If we look at lee side angle histograms here, through the flood, time starts at the top and we're increasing in time down towards the bottom. We can see that this is a discharge value here. So we're looking at the hydrograph on this right panel. We can see during this time, this is the peak of the flood. When we look at the lee side angle histograms, we can see that the lee side angles are low. They're at around 10 degrees and they increase during the peak of the flood, but they don't increase by much. Maybe the mean value increases by about 5 degrees. When we look at the bedform hysteresis here, we have discharge on the X here, and we have lee side angle, dune height, and dune wavelength on the Y. Let's just focus on the dune height really right here. If we look at the northern dunes in this middle line here, we can see that this is the mean value, and we see that we have a counterclockwise hysteresis here. When we look at the southern dunes, we don't see any hysteresis. So the largest hysteresis occurs in the northern dunes, whereas we have little to no hysteresis in the south. And we see that across the lee side angle as well. When we look at the potential for flow separation, in these graphs, time is increasing towards the right and downwards. I've highlighted the peak flood here in red. We can see that the potential for flow separation is low throughout the flood. And so this allows us to make better decisions on dredging locations and the navigational safety measures that we should take during these floods. The question still arises, why do we see bedform flow hysteresis in these northern dunes? And I think profile overlaps really help us understand a little bit more about that. If we look at a profile overlap, this is a very very nice way to see this. If we have a dune that's just purely migrating, we'll have an area of erosion on the Stas and an area of deposition on the lee side. If we color that, we'll see that red is eroded and blue is the deposited area. Now, if we look at the northern dunes, this is for the rising stage and this is for the falling stage. Flow is going from right to left here. These overlaps have a time period between them of about 20 minutes. When we look at the rising stage dunes, we see that superimposed dunes are migrating. And we can see that because we have this really quick striped pattern of erosion and deposition, which represent these superimposed dunes moving over the larger dune. When we look at the falling stage, we see that these dunes are dominated by deposition. And what's likely happening is that in the falling stage, when flow is decelerating, the dune migration decreases and the entire dune becomes dominated by sediment deposition, which results in dune growth. And so you can imagine that this is likely what's happening for all of the dunes on the northern side. And this is why we're seeing that these dunes grow during the falling stage. This is why we see this hysteresis. So to summarize, we saw that Bambi offers robust measurements of dunes from high spatial and temporal bathymetric data. From this, we see that dunes and alluvial channels have low angle lee sides and small heights compared to their flow depth. And we also see that if we think about the possible controlling mechanisms of low angle dunes, that lee side avalanches is likely not a major control. And that's because we see high angle dunes in deep flows and low angle dunes in shallow flows. And instead, the influence of sediment suspension and bedform superimposition are major controls. And there's likely a balance between the two, where when one is dominant, the other one is less likely important. When we use all of this to think about the potential flow separation potential in these rivers and in these experiments, we see that flow separation potential is lower than previous estimates in rivers and suspension dominated flows. Now, when we bring all this together, we also know that changes will happen across different grain sizes during flow hysteresis, which we saw a very quick example of, and other spatiotemporal variations that are common in rivers. And so when we think about these dunes and the formation of these low angle dunes and the processes that may lead to them, we also have to consider that that's going to all vary across all of these different conditions as well. And so with that, I'm going to summarize my research, but I want to spend a little bit of time talking about some of the other things that I've accomplished during my time in graduate school. So 5 years ago, I made a goal for myself. I said I aim to balance myself as a researcher who in the future stands on the edge of both aeolian and fluvial geomorphology and is one day capable of bridging the gap in the research. I'm very proud to say that I'm one step closer to that goal, as I've received an NSF postdoctoral fellowship to study the morphodynamics of giant dunes in wind and water, working with Jeff Nichar and Ryan Ewing. The idea that we propose is that we see that simple aeolian dunes exist in deserts, and we have compound dunes as well in deserts where we have these small superimposed dunes climbing over them. And we also know that simple and compound dunes exist in rivers. We've seen a lot of that today. So the idea is that if we can understand more about how simple dunes interact with larger dunes, how they change dune shape, and how they influence how sediment is transported, then we can use that information to understand how giant dunes in deserts move. The interesting thing is that giant dunes in deserts move really slow. It's really hard to understand how they change shape, how they react to different conditions, and how they transport sediment. And so if we can use river dunes as analogs to understand how these giant compound dunes move, then we can understand how these giant dunes are working. So I've proposed to continue using Bambi and to develop it to work in aeolian settings as well. I'm really happy to say that I ran it very quickly on a data set from White Sands, and it's working. It identifies the dunes, and the measurements are pretty consistent with hand measurements, and so I'm excited to continue developing that. The study areas that we proposed are in Algodones, California, where we have giant compound dunes, in White Sands, New Mexico, where we have simple desert dunes, and in the Mississippi River, where we have dunes that change from simple to compound. We have a few existing data in Algodones and White Sands, and we've proposed multi-beam surveys in the Mississippi River. I'm also very proud to say during my time at the University of Illinois that I created the Geoscience Camp for Girls. I did this with my peer graduate student and colleague, Aida Gulenkozy, and over 1.5 years, we developed the camp, handled all of the recruitment and all of the logistics. For the first time, we successfully brought about 30 middle school girls to our university, to our school, to learn about geoscience topics and to envision themselves as geoscientists. Since then, we've been invited to present our work towards creating this camp in a variety of venues. Most recently, I presented the journey that we took towards creating the camp at the GSA 2020 Next Generation of Geoscience Leaders, Strategies for Excellence in Diversity and Inclusion. Aida and I have also been invited to write a paper, and it is currently in review at GeoJournal. I'm also very proud to say that I was a part of the team that wrote the call for a robust anti-racism plan in the geosciences. This call was led by Dr. Henrata Ali, and it received the 2020 AGU Presidential Citation this year. I encourage you to look it up, to read it, and to consider signing it and building it into your current efforts or use it as a base to build from. The geosciences is the least diverse field in STEM, and it's going to take a lot more than words to improve that. I'm also really happy to say that I was a part of creating the GeoHydro discussion group with Roberto Fernandez and Quinn Lewis. And since then, my friend Jorge San Juan and I had led it for about 4 years. Now I'm really happy to say that it's continuing and other graduate students have decided to take it on. GeoHydro discussion group is a group that brings together geology students, geography students, and hydro students who all study things related to water, so that we can have a safe and comfortable atmosphere to discuss our research and gain peer mentorship opportunities, but most of all, to gain friends. Jorge and I are actually invited to speak on a panel in April at the AGU EPSP Connects seminar series called Building a Supportive Research Community. And so I encourage you all to join if you're interested in learning more about that. Finally, I'm very happy to say that I'm a part of the GeoLatinas. GeoLatinas is an inclusive, member-driven circular organization with the mission of embracing, empowering, and inspiring Latina women to pursue and thrive in earth and planetary sciences. In GeoLatinas, we offer several opportunities for mentorship, leadership, wellness activities, and even professional development. One of my favorites being the coding group, where about a year ago, we all came together because we wanted to learn Python. And so we created a very comfortable and safe atmosphere to learn Python together. If you're interested in learning about GeoLatinas, I encourage you to look us up on social media, but you can also ask me about it. I'm always happy to talk about GeoLatinas. And so with all of these efforts, I have a new goal. Through my research, my work in diversity, equity, and inclusion, and my work towards becoming a better teacher and mentor, I aim to become a future leader in the geosciences. Now, before I end, I want to say thank you. I want to acknowledge my funding sources. I'm funded by University of Illinois Graduate Research Fellowship, a graduate research fellowship from the NSF, and my research in the Netherlands was funded by the NSF, the NWO, TU Delft, and Deltates. I'd also like to thank my collaborators and my committee for being so awesome and helping me develop such a cool PhD project. And I'd like to thank my advisor, Jim, for giving me so many opportunities to become a better scientist. I'd also like to thank all of the awesome people that I've met in my time in graduate school and research. I value you all so much. I'd like to also acknowledge the people who have been such a big part of my life outside of graduate school and research that have kept me grounded. You all mean so much to me. And the very special few who have extended across both of those worlds, I do not know what I would have done without you. You are so amazing. Thank you for everything. I'd also like to thank the very special people who in this last year have jumped on virtual offices with me to support me and work in silence and solidarity as I finish this PhD. I'd like to thank my family, my mom, my dad, my brothers, and my grandma for always believing in me and supporting me. And I'd like to acknowledge two very important people who are sadly not here with us today, but who have contributed so much to my growth as a person, my grandpa Lupe and my mother-in-law Maggie. I know that they would both be so proud of me. Finally, I'd like to thank the best person in the world and the best partner I could have asked for, Nathan McCallum. You have supported me through everything since before day one, and I'm so proud of everything that we've accomplished and all that we've done together, and I'm so excited for what's to come. Thank you so much for everything. I couldn't have done this without you. So with that, I'd like to say thank you, and I am looking forward to your questions.
Thank you, Julia. Marvelous, and yeah, thank you for that, taking us all the way through that. Let's open it up to any questions that you might have from the viewing audience.
If you, sorry, I can't see. If anybody has a question, you can talk.
Hi, Julia, it's Raquel. I have a question, but I feel like I shouldn't ask first. Does anyone have, I have like big picture questions. Anyone have like science, like questions, burning? No?
Yeah, I saw somebody who had her hand raised, but I can't see the hand raised.
Okay, well, I'll just ask you.
Yeah.
So like, what is it about dunes? Like, what do you think they say about Earth systems or Earth processes that just fascinates you?
Yeah, I think the thing that really has driven me through this whole time is that these dunes, they record these ancient conditions. And as they move, as they change shape, they can tell us about what was happening during that time. And so what really drives me is understanding how these dunes change shape in relation to the conditions that they're forming in, what is affecting them, and then starting to figure out what are the little things that we can use in the stratigraphy, in the deposits, to tell us a little bit more about what was happening during that time. I think that's really exciting. And I think that if we can understand that across a range of environments, then we can start to extrapolate that to even different worlds, different planetary systems. And that is really what I am very excited to do with my career. So thank you for asking that, Raquel.
Julia, I've got a question.
Oh, hey, Ryan.
Yeah, congratulations. That was excellent to see. So I'm wondering, it seemed like most of the dunes you looked at were transport limited. And would you expect any of these patterns that you saw in the morphology to be affected if these were availability or supply limited dunes, which is kind of the case for most, Aeolian is giant dunes are transport limited. So I'm kind of wondering where this is going to go.
Yeah, that's interesting to think about. I do think that a lot of these are transport limited, but if we think about some of the big cases, like in the Amazon, that it's such a big channel that I think that there is a case there where we could look at whether that is a supply limited case as well. Even though the Amazon is so big and there's so much sediment being transported, when we think about just the sheer size, these are like 120 meter flow depths. And we can see that the sediment here, there are some very interesting shapes in the Amazon that are similar to what we see in these Aeolian or these big deserts, for example, like these big Barcan dunes. And so I am not sure how that's going to translate, but I think there are some cases that we can actually focus on that may be a little bit more similar than we think. Specifically in the Amazon, I think it would be a good case study to compare.
Yeah, sounds good. Let's do it.
Yeah, I'm excited.
Tom next, maybe, and then Hema. Tom first.
Thanks, Julia, for an amazing talk. That was a real tour de force. So I have a question about the rock record. So sometimes when you do research like this, you observe something profound, like you've seen with these dunes with the low angle lee sides. And then people start telling you, well, yeah, that's we've been seeing stuff in the rock record for years and we didn't know what to make of it because it didn't match expectations. How is that playing out?
Yeah, I have had that question or that discussion every time I've presented this. I've had people who are like, I've looked at dune, deposits for the past 20 years, and I always saw these low angles and I just didn't know what to think of it. So I just kind of brushed it off. And I think it's exciting that I'm starting to make these comparisons with, such a big team of these flow conditions and the processes that are leading to their formation, because I think that it allows us to really look a lot more into what these low angle dunes are telling us. Number one, it tells us if we see really big cross sets that, we're looking at a really big river, and these new flow depth relationships allow us to make better recommendations of what these ancient flows looked like. We can see that past relationships may be pretty underrepresented or underestimated. And so I think that's really exciting. In addition, because we have these low angle dunes, some other researchers, for example, Renato País de Almeida, he's looked at how superimposed dunes can climb down these larger dunes and what that may look like preserved in the rock record. So for example, if we see superimposed dunes climbing down, that may be preserved as high angle cross strata bounded by low angle bounding surfaces. And that tells us a lot about the presence of superimposed dunes, but also what the conditions were there in that case. And so I think this is really a really exciting time to start taking this to the rock record and start making some reinterpretations. Thanks, Tom.
Wow.
Thanks, Tom. Just think about time. Hima, do you have a question?
Hi, Hima.
Hi, amazing talk. I was so inspired. And as you know, I think a lot about how sediment is moving in rivers and how they make it to floodplains. And I'm excited that maybe you can learn more about sediment transport from the actual from the actual deposits themselves. So similar to Tom's question, is there a particular location where you think we can figure out if a river is moving most of its sediment as suspension versus bed load and rock record?
In the rock record? Oh,
Yeah.
Wow. That's a great question, Hima. I think that you have way better understanding of like ancient deposits in places. I need to do more research in this. What I can say is that I know there's been previous work, looking at the presence of an Amazonian scale river in Illinois during the Carboniferous period. And so I know a lot of people in our research group have studied that, specifically Kalen, who was a master's student. He was looking at ancient deposits in southern Illinois, trying to sort of work out maybe what deposits may represent this ancient Amazonian like river with these low angle cross stratification. And so I think that would be a really cool place to start with. But I know from talking to a lot of different people that there are a lot of places that this has been seen. I think recently I was talking to a professor at A&M, Nicholas Perez, and he was like, I saw these in my research in Peru. And I was like, let's go to Peru. So we'll see.
That's amazing. Looking forward to that research.
Yeah, Mariel, you can go ahead.
Hey, that was a great talk. I was wondering if you had any ideas about like dunes and smaller rivers. I'm specifically thinking about the like red and blue erosion and deposition patterns like that happen on like a storm to storm timescale. Any thoughts?
Yeah. Small rivers is this gap that we have right now, right? It would be very cool to start looking at small rivers and see if we can see similar dunes, similar interactions, things like that. So far, not yet. I can say that we're working on it. We're working with a few people who have some really cool multi-beam data. Corey Consor has been doing really awesome surveys in very shallow, small rivers. So I have to say, I don't know yet, but stay tuned and I will be sure to share it with you. Thanks for asking. I'm happy that you're thinking similar things because that means that that's going to be a cool paper to make.
That's awesome. Thank you.
Okay, just looking at time again and thinking about the next stage in today for Julia in terms of the committee. Are there any last questions just before we go?
I don't see any hands.
I do have one more, Julia. I swear it's short.
Yeah.
So what about your experiences, like specifically I'm interested in this geo-hydro like peer group you made, like inform the kind of leader you now aspire to be? Like what would you do as a faculty member or mentor, that's informed that experience? Yeah,
thank you for asking that, Raquel. I've been thinking about that a lot. I look back on the things that I've done in graduate school, creating the geo-hydro group with some of my friends and doing geolatinas and even all the little things that Jim had mentioned at the beginning. And I think what really defines me and how I want to move forward in my career as a leader is that my focus is creating community, creating places where students and researchers and professors can come together, have supportive relationships, offer mentorship, and mentorship doesn't look the same for every person. You can also have, a lot of opportunities for peer mentorship, but really that all happens when you create a positive and comfortable community. That means supporting people, creating equitable opportunities for everybody, dealing with people who do not believe in that, and fighting for justice so that we can all be better. We can all be better scientists, and we can all feel like we can contribute to science in the same way. I think that's what really is going to push me through my career and how I'm going to try to be a leader in the future. Thanks.
Okay, well, let's thank Julia very much again for a wonderful talk and resume of what she's done over the last years. And thank you again from all over the world, all different backgrounds. Thank you for tuning in today, and look forward for hearing more of what Julia's got to come in her postdoc when she moves down to Texas A&M with Ryan. Okay, so take care, everybody.
Thank you all. Thank you so much.
Thank you, Julia.
Great work, Julia.
Thank you. Thank you.
And just for the committee, we'll meet on the other Zoom link that I sent around. And Julia, what we'll do is we'll just meet committee. If we meet in, let's have a 5-minute gap. Let's have a 5-minute break. Meet about let's say about 12:15. And then Julia, what I'll do is I'll send you a text, and then after we have an initial chat, get you to join in on the meeting. Okay.
Great.
Be about 12:20. Okay.
Okay.
Okay. So Jim, I had difficulty logging into this meeting now. So if I'm not there, then hang in, and then
okay.
I'll be there.
Okay. Okay. Yeah. Hey, try that now, and I'll open the meeting now just to make sure you can get on. Okay.
Yeah. Okay.
Okay.
So I'll close this one.
Yeah. Okay. Take care all.
Bye.
All right.
Thanks,